Come on, my dears, let us begin with chapter number 5. The title is Atoms. Fine. Chapter is really very interesting. In the beginning of chapter, in the very first article, they have given preface, that is introduction, in which they have included certain facts, certain inventions, discoveries made by different scientists over the period of years in the early development of science. Fine. But as such, nothing is being asked from such introduction part as far as board examination is concerned. Majority of the times they don't ask. Then also we should not take any chances. So we will prepare this introduction also. But what I suggest to you, you should prepare remaining part of the chapter first, and once you are satisfied with that preparation, then only you should touch this article. If time permits you, you can prepare this introduction also. Okay? So let us see those facts one by one. Come on, number 1. In the beginning of 19th century, in the year 1803, there was a scientist, Mr. John Dalton. He showed that the smallest part of an element is atom. So what is atom? Smallest part of an element. Fine. He showed that these atoms are indivisible, means you cannot divide it. You cannot have anything smaller than atom. Okay, fine. It is the atom which takes part in the chemical reaction. Okay, fine. And if you are talking about a given element, then for a given element, it's all the atoms are identical. Okay, fine. Second fact, look here. It was Mr. Jean Perrin who had found negatively charged electron. Mr. Jean Perrin had discovered negatively charged electron. Okay. Later on, in the year 1912, Mr. Robert Millikan had measured this charge of electron, and you know it is shown by symbol small e. It is also called fundamental charge or quantum of electric charge, or you can say elementary charge, and it is by value 1.602 into 10 raised to minus 19 coulomb. Correct? Fine. Then Mr. J.J. Thomson, he had measured ratio of charge of electron to the mass of electron, that is E upon m, was found out by Mr. J.J. Thomson. You know, total charge upon total mass will give you charge per unit mass. Charge per unit mass. It is also called specific charge, and specific charge of electron is 1.7589 into 10 raised to 11 coulomb upon kilogram, which you studied in 3rd semester. Correct? Remember it. Fine. Then Mr. Henry Becquerel had invented one phenomenon accidentally. That phenomenon was known as radioactivity. Radioactivity. It was invented by Mr. Henry Becquerel. But then later on, majority of the research was carried out by two scientists, Madame Curie and Rutherford. Madame Curie and Rutherford. Fine. And then further research proved that these elements which show this property, that is property of radioactivity, they emit certain specific radiations which are called radioactive radiations. And these radioactive radiations consist of negatively charged electrons and positively charged alpha particles. Okay. Later on, scientists proved that the constitution of an atom is due to negatively charged particles and positively charged particles which are accommodated inside the atom. Okay. So structure of atom is grateful to negatively and positively charged particles. Okay, fine. Negatively charged particles are electrons, positively charged particles are protons. Okay. So negatively and positively charged particles, they compose the atom. Okay, fine. Then because negative and positive charge is present inside the atom with equal amount, then naturally atom will be electrically neutral. Atoms are electrically neutral because each atom contains same amount of positive charge, same amount of negative charge. Okay, fine. Then solid substances, liquid substances and gases with high density, atoms of solid substances, liquid substances and of those gases which have very high density, you know what they do? They emit radiations with continuously changing wavelengths. So they emit continuous radiation, that is having wavelength ranging continuously, changing continuously. Okay, fine. This is called continuous emission, where you find all wavelengths are present. Fine. But then if you consider atoms of gas having very low density, if you excite them, then we find that they emit radiations with some typical, some discrete values of wavelength only, because only certain wavelengths are emitted. Radiations are emitted with certain wavelengths only. We call this emission as non-continuous emission, where all the wavelengths are not present, only certain wavelength values are present. Okay, this is called non-continuous behavior of an atom. Fine. And now this all atoms, you know, they also absorb the radiations depending upon their selection. See, if you make incidence of so many wavelengths, correct, which are changing continuously, then atom absorbs only certain wavelength radiation only. If you make incidence of radiations having continuously changing wavelength on an atom, you know what does atom do? It absorbs only certain radiations with certain wavelengths only. It does not absorb all the radiations with all the wavelengths. No. So what I mean to say, absorption is also very selective. Emission is also selective. Absorption is also selective. Only certain wavelengths are emitted, only certain wavelengths are absorbed. This behavior is non-continuous behavior of an atom. Fine. And from all these facts and so far whatever we have discussed, we arise, I mean so many questions are arising in our mind. Let us make a list of few questions. What are the questions based upon these facts I am showing you? First, of what atom are made up of? Atoms are made up of what? Atoms are made up of what? What is inside the atom? Okay, first question. Second question is that how is the arrangement of charges in an atom? What is the arrangement of charge inside the atom? Third question is this: why are atoms stable? Correct? What is the reason for stability of an atom? Number 4, why do atoms emit radiations with definite wavelengths depending upon type of element? Why not all the radiations with all the wavelengths? Why radiations with certain wavelengths only are emitted from an atom depending upon type of element? Okay, that is the question. And last question, just now we have noticed the non-continuous behavior of an atom. Then we think, is there any similarity, is there any analogy between this non-continuous behavior and the photon theory which is proposed for explanation of black body radiation? Is there any similarity between these two? That is the questions. Okay, fine. Now this much is included in the introduction in the chapter. Now real chapter begins now. Let us consider now. Thomson's plum pudding model or Thomson's watermelon model. How is the composition of an atom? What is the constitution of atom? Very first theoretical model was proposed by Mr. Thomson. He suggested that Perhaps the structure of atom is like watermelon, in which majority volume is occupied by pulp of watermelon. Pulp of watermelon, which here I have shown with a pink shade. Okay, this is the pulp. Okay, and inside that watermelon we find seeds of watermelon. Correct. So what Mr. Thomson had made the comparison, he said that where we find pulp of watermelon, there is the distributed positive charge, and where we find seeds in the watermelon, there are negatively charged particles, say electrons. Okay, this is the theoretical model proposed by Mr. Thomson, called plum pudding model or watermelon model. Okay, now this model failed completely because it had so many drawbacks. Which are the demerits, which are the drawbacks, what are the failures of this Thomson's model? I am showing you. First, stationary system of charges is not possible. Mr. Thomson said that these charges are stable. No, they cannot remain stable. If you have a system of charges, might be all of them are positive or all of them are negative, or some positive, some negative, they cannot remain at rest at the same positions. So a stable system of charges is not possible. So this is the first drawback. The model which Thomson had proposed, in which he had assumed the stationary distribution of charges, which is in practice not possible. Second thing, we know that if here is positive charge, here is negative charge, there exists very strong attractive Columbian force. An electric force which obeys Coulomb's law is called Columbian force, and because of that attractive force, actually these charges should be accelerated, and Mr. Maxwell had proved that accelerated charge emits energy out of it in the form of radiation. Correct? Fine. If it is so, then accelerated charge would emit energy. Then question arises, how this atom can emit radiation continuously? How it can be the source of production of electromagnetic waves continuously? How it can emit the energy? That is the question. And if at all we assume that, suppose it is possible, then also question arises, why radiations are emitted with certain specific wavelengths only? Why not all the wavelengths? Correct? That is the question. So this is how this Thomson model completely failed, because it could not satisfy the practical expectations. Correct? Look, then only one merit, only one good plus point for Thomson's model was that it was Mr. Thomson who had guessed the size of an atom very first. He had guessed that diameter of atom, size of atom, perhaps is of the order of 10 raised to minus 10 meter. Nearly 10 raised to minus 10 meter may be the diameter of atom. That is what he had said first. Fine. Now, when Thomson's model failed, Mr. Rutherford had proposed new model for structure of atom. What was Rutherford's atomic model? Just to prepare that model, Mr. Rutherford had performed a series of experiments, later on it became famous with the name Rutherford's alpha scattering experiments. Actually speaking, Mr. Rutherford had given proper theoretical explanation behind the practically observed observations. Actually, observations taken practically majority by Mr. Geiger, who happened to be colleague of Rutherford, and Mr. Geiger was accompanied by his student, and student's name is Mr. Marsden. Mr. Geiger and Mr. Marsden, they had collected so many practical observations. Mr. Rutherford happened to be student of J.J. Thomson, and Marsden happened to be student of Geiger. Which observations were taken by Geiger and Marsden? Let us see now. they had used one definite experimental setup. What was that experimental setup? I am showing you. Here is we have, come on, source of alpha particles. First of all, let me tell you what is alpha particle. It is the central part of helium atom. Central part of helium atom. It contains 2 protons and 2 neutrons. A composition of 2 protons and 2 neutrons is known as one alpha particle. Okay, fine. Now, these are the alpha particles emitted from this radioactive element. It is a source of alpha particles, so I have written here S. Okay, fine. Now, what is the radioactive element? It is 83 bismuth 214. 83 is the atomic number. Bi indicates bismuth element. 214 is called atomic mass number. Atomic number gives you number of protons, correct? Then, come on, 214 is atomic mass number, which gives you total number of protons and neutrons. Okay, fine. Now tell me, these are the alpha particles emitted from this source. They have kinetic energy, which you must remember, 5.5 million electron volt. 5.5 million electron volt. 1 million or 1 mega, it is 10 raised to 6, and 1 electron volt is 1.6 into 10 raised to minus 19 joule, correct? Fine. Now, out of this alpha particles, we want very fine, very narrow pencil beam of alpha particles. Just to have a very sharp beam of alpha particles, we allow these alpha particles to pass through these 2 bricks made up of lead. So, we place 2 pairs of lead bricks, between which there lies very narrow gap, very narrow, and that very narrow slit is there through which these alpha particles are passing, and then after they form very narrow beam of alpha particles, very sharp beam. Fine. Here we have golden foil, that is extremely thin sheet of gold. Okay, fine. Its thickness is 2.1 into 10 raised to minus 7 meter. Fine. So, this is golden foil. Now, these alpha particles are made incident on this golden foil. Wait. What do you mean by scattering of alpha particles? I am showing you. Before this experiment, there was a primary observation taken by Rutherford. What did he take? He had taken one chamber, and inside the chamber he had kept one slit, and through the open gap in the slit he had passed alpha particles. Behind the slit he had put one fluorescent screen. He had kept one photographic plate. And photographic plate is black. On whichever part alpha particles were made incident on the photographic plate, that much part turns out to be white. But when he had observed the edges of that white part, he found that edges are not very sharp. Okay? And then after, what Mr. Rutherford had done, he had evacuated that chamber. So, he had removed completely air from that chamber. He had removed air completely from that chamber. So, he made that chamber evacuated, and then after he had made alpha particles incident on the same slit. Once again he had obtained impression over photographic plate. Now that impression had quite a sharp edges. What does it mean? That earlier when air was present inside the chamber, alpha particles happened to collide with atoms of air, and after a collision they are just getting deviated in all the directions. This process of deviation after collision is known as scattering. So, earlier alpha particles were getting scattered by colliding air atoms and molecules, and that's why the edges of the impression obtained on the photography plate were not very sharp. And then after, when the chamber was evacuated, there was no scattering, and at that time he got the edges very sharp. Okay, fine. The way alpha particles got scattered by air molecules, atoms in that chamber, same way alpha particles will be getting scattered here also. Listen, some of the alpha particles may penetrate this golden foil, and after penetration they will be here, correct? They may go in different directions like this. And some of the alpha particles which undergo a very strong collision, they are getting scattered in this backward directions. Fine. Now this is the initial direction of velocity, direction of initial velocity of alpha particles. Suppose particular alpha particle goes in this direction, suppose. Then this is scattered direction, this is original direction. Angle between original and scattered direction is called angle of scattering, shown by symbol theta. Now what we want? We want number of alpha particles getting scattered in a definite direction, and just to find out that number, we use here one specific device. It is called detector. The detector, actually it is a microscope having fitted with some fluorescent screen at the front part, and that objective is covered by one screen which is called fluorescent screen. It is normally made up of zinc sulfide, and there we get scintillations. Now let me explain you two words. What is called scintillation? What is called fluorescence? Whenever energetic particles are made incident on a screen, say zinc sulfide, then at the point of incidence we get a flash of light for a very short time. Such flashes of light observed for very short time are called scintillations, And this phenomenon in which we obtain scintillations, this phenomenon is known as fluorescence. What is it called? Fluorescence. Okay. So this screen having the property of fluorescence is called fluorescent screen. So zinc sulfide screen is a fluorescent screen. Fine. Now Mr. Geiger and Marsden had rotated this microscope through different angles, and in different directions what is the number of alpha particles is getting scattered. That number they had found out practically, and then after they had plotted one graph of number of alpha particles versus angle of scattering, and from the practical observations they had plotted some dots, some points in the graph, and then after the curve joining these points is this curve. Okay, fine. Now these are the points which indicate observations taken practically. You try to remember some 2-3 observations. Very simple it is. Number of alpha particles getting scattered in a direction making angle 15 degree with the original direction was found to be approximately 10⁵, that is 1 lakh. Number of alpha particles getting scattered by angle 150 degree was found to be roughly 80. And with the surprise of everybody, when Geiger and Marsden had performed experiment for a very long time, they got one alpha particle undergoing maximum scattering, and at that time the angle of scattering was maximum 180 degree. How? I am showing you. See, this is the atom in this golden foil I have shown here. This is the incident alpha particle. Now this, in this direction, if it is moving this way, then in this direction it has its initial velocity. Fine. After a strong collision with this atom of gold, this alpha particle suppose takes U-turn. Suppose it starts moving now in this direction, that is, in this direction it has its final velocity. In this direction there is initial velocity, in this direction there is a final velocity. So this is angle of scattering. Angle between directions of initial velocity and final velocity, this is called angle of scattering. You can see it is 180 degree. But number of alpha particles undergoing maximum scattering was very small. Out of 10,000 alpha particles approximately, the number of alpha particle undergoing scattering by angle 180 degree was found to be just one out of 10,000. Okay. Now, these were the observations taken practically. Mr. Rutherford had derived one formula of number of alpha particles getting scattered in a definite direction with definite angle of scattering. What was that formula? I just written here. I'll just tell you the interpretation of each symbol, but in textbook they have written that this formula is just for the sake of knowledge only. You are not supposed to remember. Okay? That formula is this: n equals to n0 ns. N equals to n0 ns multiplied by z square upon mb square into 1 upon sine of theta by 2 whole raised to 4. I repeat. Capital N equals to capital N0 into small n into small s into z square upon mb square into 1 upon sine of theta by 2 whole raised to 4. Repeat. N equals to N0 ns into z square upon mb square into 1 upon sine of theta by 2 whole raised to 4. Just give me interpretation of each symbol. Come on. This is the number of alpha particles getting scattered in a direction having angle of scattering theta. Come on. N0 is total number of alpha particles made incident. Small n is number of atoms per unit volume in the golden foil. What is small s? Thickness of golden foil, which we had taken 2.1 into 10 raised to minus 7 meter. Okay. What is Z? Atomic number of element, which is gold. For auric Au, the atomic number is Z equals to 79. What is small e? Charge of one proton or magnitude of charge of one electron. What about m? It is mass of one alpha particle. V is the velocity of alpha particle. What about theta? Angle of scattering. Correct? Fine. Now, using this theoretically derived result, when Mr. Rutherford had plotted graph of n versus theta, that theoretical graph is just superposing on this graph which is obtained practically. If theoretical and practical graphs are overlapping on each other, it shows the correctness of this formula. This formula was very much correct. Okay, fine. Mr. Rutherford had found the trajectory. He had determined the trajectory of alpha particle before and after scattering. The trajectory was determined by Rutherford. But for finding the trajectory, he had used two results. One is Newton's second law and another is Coulomb's law. Another is Coulomb's law. Now listen, when alpha particle is made incident on the atom of gold, then what can be the Columbian force? This much can be the Columbian force. Look here, F equals to K Q1 Q2 upon R square. You know Coulomb's law. Instead of small k, I written here 1 upon 4 pi epsilon 0. Q1 is say charge of alpha particle, which is double than charge of proton. It is 2 into E. And here I am writing positive charge of gold atom. It is Z into E, where Z is atomic number of gold, which as I told you 79. E is the magnitude of charge of one electron. Fine. And R is the distance between alpha particle and the center of gold atom. Okay, fine. Now, how would you explain this maximum angle of scattering 180 degree? How would you explain? Mr. Rutherford had given very nice, very satisfactory explanation for maximum angle of scattering. How? I am showing you. Look, consider this as atom of gold. Okay. Just for a while you assume that almost total mass of atom and total positive charge of atom are suppose concentrated in very tiny central part of an atom. Just assume. Okay. If total mass, almost total mass and total positive charge are considered to be concentrated in a very tiny central part, then what will happen? I am showing you. Consider this alpha particle which is made incident on this atom. Suppose center of atom and center of alpha particle lie on the direction of initial velocity. I repeat, suppose these two centers lie on the direction of initial velocity of alpha particle. Fine. Now tell me, when alpha particle is just approaching in this direction, its initial velocity is aligned along this line, and suppose after undergoing collision with this atom exactly at the center, it bounces backward just in opposite direction. So this is the direction of initial velocity, this is the direction of final velocity. This angle of scattering you can see 180 degree, correct? But such a strong collision, such a maximum scattering would be possible provided you assume that almost total mass of an atom and its total positive charge are concentrated in the very tiny central part. Yes, that is true. Then only this maximum angle of scattering was possible. Now that very tiny central part of an atom in which almost total mass of atom can be considered to be concentrated and its total positive charge is concentrated, that very tiny central part is known as nucleus. So the introduction of nucleus was given by Rutherford. Okay, fine. So this tiny central part now onwards we will call nucleus. Fine. Now let us define two more definitions. One is impact parameter, another is distance of closest approach. Let us see one by one. First of all, let us see what is called impact parameter. I am showing you. Here is atom of gold. Here is the center of nucleus. Fine. Suppose you consider 3 alpha particles which are made incident on this atom. Particle number 1, 2, 3. For this first particle, its initial velocity is directed along the same line which passes through centers of alpha particle and atom of gold. For this alpha particle, it so happens that it undergoes maximum scattering. It is made incident this way, getting bounced backward, and then this angle of scattering is maximum. It is 180 degree. Let it be theta 1. Fine. For second alpha particle, its initial velocity is in this direction, correct? But as it approaches this way, after just going closer to this nucleus, you know nucleus has a positive charge, alpha particle is also positive charge particle, so there will be some repulsion between them, and after getting repelled, suppose that alpha particle is approaching in this direction. So in this direction there lies final velocity. In this direction there was initial velocity, in this direction there is final velocity. This angle gives you angle of scattering, let it be theta 2. Now tell me, this is the direction of initial velocity of incident alpha particle, and this direction has perpendicular distance this much from the center of nucleus or from the center of atom. This much perpendicular distance itself is known as impact parameter, shown by symbol small b. How would you define it? perpendicular distance between the direction of initial velocity of alpha particle made incident on an atom from its center is called an impact parameter. Perpendicular distance of direction of initial velocity of alpha particle made incident on an atom from the center of that atom is called an impact parameter shown by symbol small b. I repeat, perpendicular distance of direction of initial velocity of alpha particle made incident on an atom from the center of atom is called an impact parameter shown by symbol small b. For third alpha particle, now you can see impact parameter is this much, because this much gives you perpendicular distance between direction of initial velocity of third particle and center of this atom. This much is the perpendicular distance called impact parameter. Now, because this particle passes by this atom with some larger distance than this, then it undergoes less scattering because of less repulsion, because of more distance. Then this angle is less. This angle is less. So what have we noticed in the figure? That as impact parameter decreases, angle of scattering goes on increasing. Compared to B3, B2 is less. Compared to B2, B1 is less. B1 less than B2 less than B3. But then when it was B3, theta 3 was minimum, and then compared to B3, B2 is less. Compared to theta 3, you can see theta 2 is more. Compared to B2, B1 is less. Compared to theta 2, theta 1 is more. I mean to say, as impact parameter decreases, angle of scattering goes on increasing. That's what I have written here. As value of B decreases, come on, angle of scattering goes on increasing. Fine. Maximum angle of scattering is 180 degree. It would be possible for this alpha particle, and for this alpha particle, because its direction of initial velocity is aligned along the same line joining the centers of alpha particle and the atom, then perpendicular distance would be 0. And when perpendicular distance is 0, you can say impact parameter is 0. And when impact parameter is 0, then only alpha particle can undergo maximum scattering. Say for this alpha particle, come on, when it is made incident on this atom along the direction which is aligned along the line joining the centers of alpha particle and atom, then for such alpha particle impact parameter is 0. And at that time it is made incident this way, coming back in the opposite direction. So this angle of scattering, you can say it is 180 degree. And at that time such alpha particle manages to go closest to the nucleus. And when it goes closest, the minimum distance between incident alpha particle and the center of atom is called, that minimum distance is called distance of closest approach, shown by symbol R0. Definitely value of R0 will depend on kinetic energy of this incident alpha particle. If you make alpha particles incident with more kinetic energy, then they will go more closer to the atom. And as it goes closer and closer, then this distance would decrease. So how much value of distance of closest approach R0 will be, that depends on kinetic energy of incident alpha particle. More is the kinetic energy, smaller is the distance of closest approach. Fine. And from these observations, we have approximated the radius of nucleus, correct? Among the values of R0, whichever is the minimum, that would indicate common distance between these 2 points, and distance between these 2 points for such a nucleus gives you its radius. So radius of nucleus is approximated to be 10 raised to minus 15 meter, of the order of 10 raised to minus 15 meter, that is 1 femtometer. Femto means 10 raised to minus 15. Okay. So very first estimation regarding radius of nucleus was given to us by Mr. Rutherford through his experiment on alpha scattering. So what is the conclusion of Rutherford's alpha scattering experiment? Conclusion is that almost total mass of an atom and its total charge, total positive charge are concentrated in very tiny central part of an atom called nucleus, correct? If the positive charge of atom is spread over the entire volume, then it cannot repel this alpha particle so strongly, then you cannot have angle of scattering 180 degree. But practically we get angle of scattering 180 degree. That is possible only if total positive charge and almost total mass of atoms should be concentrated in the very tiny central part, which is called nucleus, correct? Fine. Come on now, just remind me two definitions again. First of all, what is called an impact parameter? Tell me. Perpendicular distance between the direction of initial velocity of incident alpha particle and center of an atom is called an impact parameter. I repeat, perpendicular distance between the direction of initial velocity of alpha particle made incident on an atom and the center of that atom is called an impact parameter, shown by symbol small b. It is some sort of distance, so its unit would be meter. Okay, fine. What is another definition? Distance of closest approach. Distance of closest approach. When alpha particle is made incident on an atom with a zero impact parameter, the minimum distance between alpha particle and the center of that atom is called distance of closest approach, shown by symbol R0. It is also some sort of distance, and distance of closest approach will depend on how much is the kinetic energy of incident alpha particle. More is the kinetic energy, smaller is the value of distance of closest approach. Got it? Once again, when an alpha particle is made incident on an atom with a zero impact parameter, comma, the minimum distance between alpha particle and center of that atom is called distance of closest approach, shown by symbol R0. Correct? Fine. Come on, my dears. Now, let us see which model was finally proposed by Mr. Rutherford regarding atom. That Rutherford's atomic model is very simple. What did he argue? He said that almost total mass of an atom and total positive charge of an atom are concentrated in very tiny central part of an atom called nucleus. And so far electrons are concerned, Mr. Rutherford had opined that electrons are revolving around nucleus in any possible circular orbit. Yes, this is called Rutherford's atomic model. But when he said that electron can revolve in any possible circular orbit around nucleus, that argument was very wrong. Why it is wrong? I am showing you. Say, if electron performs circular motion, you know electron is a charged particle, and whenever charged particle performs circular motion, you know circular motion is an accelerated motion. So right now this charged particle performs an accelerated motion, and don't you know, whenever any charge performs an accelerated motion, it emits energy out of it in the form of radiation. Fine. So as this electron will go on losing the energy, that energy should continuously be emitted. If it is a continuous emission of energy, then we should have all continuously changing wavelengths. But practically we find that whenever we have atomic radiation, that is radiation emitted from atom, it consists of certain specific wavelengths only. It does not consist all wavelengths. And second difficulty is that, look, if this electron while revolving around the nucleus goes on losing energy, then its own energy will decrease, and then it will come closer and closer to this positively charged nucleus because of electrostatic force of attraction, and then it would move on such a spiral path. And as it moves on spiral path, you can see radius is going on decreasing gradually, and as it goes closer and closer to the nucleus, its speed goes on increasing, and finally with tremendous high velocity it will enter in the nucleus. So it will simply break that nucleus. If nucleus is getting broken, then nucleus does not exist. When there is no stable nucleus, then there cannot be any stable atom. So I mean to say, according to Rutherford's atomic model, every atom after some time will become unstable. That is what this model suggests. But actually all the atoms are stable. So stability of atom cannot be explained using Rutherford's atomic model. This fact gives you its drawback. What is drawback of Rutherford's atomic model? Stability of an atom cannot be explained using Rutherford's atomic model. Got it? Fine. Later on, new model was proposed by Mr. Niels Bohr, and that model is quite better than this model. In that model, this drawback is removed, about which we will discuss in the next period. But at present, you kindly read this statement of first illustration. Come on, read it. Tell me. One alpha particle is made incident on the nucleus of gold, atom. Fine. As this alpha particle, you know what is alpha particle? It is nucleus of helium atom. And inside the nucleus of helium atom, there are 2 protons and 2 neutrons, among which 2 neutrons have no charge, and charge of 2 protons will become charge of alpha particle. Charge of 2 protons means 2 into E. Got it? Now, as this alpha particle approaches closer and closer to this nucleus, because this nucleus has positive charge, it would repel this approaching alpha particle. And though repulsive force is there, this alpha particle manages to go closer and closer naturally. While approaching closer, this alpha particle will require to do work against this repulsive force. And as it does this work, its kinetic energy will be utilized in doing that work. Finally, kinetic energy decreases to 0, and the moment kinetic energy becomes 0, for a moment velocity also becomes 0. When velocity of alpha particle has become 0, there is a minimum distance between alpha particle and center of nucleus, and that minimum distance itself is known as distance of closest approach. Let it be R0, which we require to find out. Okay. Apply law of conservation of mechanical energy. Come on, initial kinetic energy plus initial potential energy should be equal to final kinetic energy plus final potential energy. Now, initial kinetic energy I have kept as it is. What about initial potential energy? I should take 0. We assume that alpha particle is coming from very far, and when initially it was very far, you can say it was out of the electrostatic field of that atom, correct, and of that nucleus. So when it is out of the electrostatic field of that nucleus, naturally there won't be any electrostatic potential energy. So initially there is no storage of electrostatic potential energy, initial potential energy is 0. Final kinetic energy becomes 0 because for a moment this alpha particle has come to rest. So final kinetic is 0. What about final potential energy? Don't you know, if 2 point charges Q1 and Q2 are separated by distance r, what is the electrostatic potential energy of such a system? You must remember the formula K Q1 Q2 upon r. Only r, don't say r square. K Q1 Q2 upon r. But instead of K, I am putting 1 upon 4 pi epsilon 0, right? Q1 into Q2 upon r. Q1 is charge of alpha particle, which is 2e. Q2 is charge of this nucleus of gold atom. It is 79 into E, because 79 is the atomic number of gold. Fine. So Q2 is 79 into E upon R. Instead of R, I am putting R0. Now just put up all the values. What is initial kinetic energy? They have given 7.7 million electron volt. 1 million electron volt is 10 raised to 6 electron volt. So I should multiply by 10 raised to 6. But then yet you have to convert electron volt into joule. Don't you know 1 electron volt is 1.6 into 10 raised to minus 19 joule. So I am multiplying by 1.6 into 10 raised to minus 19. What is this? This is small k, and small k value you must remember 9 into 10 raised to 9 Newton meter square upon Coulomb square. 9 into 10 raised to 9 Newton meter square upon Coulomb square. This 2 as it is. Magnitude of charge of electron, everybody knows 1.6 into 10 raised to minus 19 Coulomb. This 79 as it is. Again magnitude of charge of electron, as I said, 1.6 into 10 to minus 19 Coulomb divided by R0 as it is, which we require. Now simplify, find out the value of R0. It comes out to be 30.3 into 10 raised to minus 15 meter. But 10 raised to minus 15 meter is known as 1 Fermi, and symbol of Fermi is small f small m, or you may say it is 30.3 femtometer. 30.3 femtometer. Don't you know femto? Femto means 10 raised to minus 15. Okay. Deci, centi, milli, micro, nano, pico, femto, etto, zepto, yocto. Respectively 10 raised to minus 1, 10 raised to minus 2, 10 raised to minus 3, 10 raised to minus 6, 10 raised to minus 9, 10 raised to minus 12, 10 raised to minus 15, 10 raised to minus 18, 10 raised to minus 21, 10 raised to minus 24. In that, femto means 10 raised to minus 15. Got it?